In this video, we're going to talk about the next variation on a theme in this idea of partial fractions. Previously, we had talked about what to do if you're looking at the integral of a rational function in which the denominator can be split up into distinct linear factors. Today, we're going to look at what do you do if you have linear factors in the denominator, but some of them show up more than once. For example, x over the quantity x minus 1 times x minus 2 quantity squared. If you try the kind of decomposition that we've tried before, a over x minus 1 plus b over x minus 2, it turns out to be impossible. Clear the fraction in the usual way. I have two special numbers, x equals 1 and x equal 2, and there's going to be a problem here. If I evaluate this equation at x equal 2, the left-hand side obviously is 2. The right-hand side is a times 2 minus 2 squared plus b times 2 minus 1 times 2 minus 2. It turns out that for this to work for x equal 2, it would be necessary that 2 equals 0, which obviously isn't true. It turns out that what we have to do is we'll have a sum of individual terms. If I have a non-repeated linear factor like the x minus 1, I'll just do the usual thing. If it were only one power of x minus 2, I would then have plus another constant b over x minus 2. In the case of having two factors of x minus 2, I'm going to need an additional factor c over x minus 2 squared. Clear the fraction in the usual way. I have two special numbers, 1 and 2. So I'll take one of these two special numbers and evaluate my equation at that x number. If x is equal to 1, then 1 must be a times negative 1 squared plus 0 plus 0. On the other hand, if x is 2, the first two terms are 0. 2 must equal c times 2 minus 1. 2 must equal c times 1. C must be 2. I've used up all of my special points though, so to determine constant b, I'm going to have to do something else. If I write in what I know already, that a is 1 and c is 2, I get this simplified formula. This is supposed to be true no matter what x is. There's two different ways that I can approach this. One is just to pick some random value of x other than 1 or 2 and evaluate this expression at that x value. That should tell me what the b is. And then there's another way that I could look at this, but we'll do the first one first and then look at the second one. Let's let x equal 0. The left-hand side is 0. Negative 2 squared is 4. Negative 1 times negative 2 is 2. 0 minus 1 is negative 1. Inserting this information into our equation for x equals 0, we find out that b is negative 1. Now, an obvious concern is, what if someone picked a different x number and got a different b number? So instead of doing it that way, I could also do it this way. Algebraically expand everything and collect like terms in the power of x together. It must be true that x is 1 plus bx squared plus negative 2 minus 3bx plus 2 plus 2b. 1 plus b has to be 0 because there's no x squared term on the left-hand side. On the other hand, negative 2 minus 3b is the coefficient of the x term, and over on the left, the coefficient of the x term is 1. Negative 2 minus 3b must be 1, otherwise the coefficients of those terms won't match. There is no constant term over on the left. The constant term on the right is 2 plus 2b. That number must be 0 if the left-hand side and the right-hand side are always supposed to be the same thing. Potentially, there could be a conflict here. One of these equations might say that b takes on a certain value, while one of the others might produce a different value. If that happened, that would tell me that there is no solution of this type, but luckily that doesn't happen in this case. If I look at each one of these expressions, the first one obviously says b is negative 1. The second one says negative 3b is 3, which says that b is negative 1. And the third one says that 2b is negative 2, and that tells me that b is negative 1. So we actually get the same result that we had before. Once we have that splitting up into simpler fractions, the partial fraction decomposition, integrating x over x minus 1 times x minus 2 squared is easy. These are routine calculations. They're left to the viewer as an exercise. Another thing we could have done in this problem is not use any special x numbers at all. Just look at the compare coefficient idea. We're going to multiply everything out and then group all the x squared terms together, all the x terms, and all the constant terms as well. I'm going to insist that the coefficient of the x squared piece be 0, the coefficient of the x bit be 1, and the coefficient of the constant term be 0. That's going to give me 3 equations involving the numbers a, b, and c. There is no x squared term on the left. A plus b has to be 0, otherwise those terms are not going to match. C minus 4a minus 3b must equal the coefficient of the x term on the right, which is 1, and 4a plus 2b minus c must be 0. This gives me a set of 3 equations in 3 variables. I should be able to solve this. If you look at the top equation, that says that a and b are negatives of each other. I could write b equal negative a or a equal negative b, as I like. I'll write b equals negative a. In the other 2 equations, every place where I see the letter b, I'm going to replace it with the negative of a. Then I'll simplify these 2 equations. The result will be 2 equations that have only a and c in them. Then I'll try to solve for a and c. Once I know what a is, b will be the negative of a. After simplifying, I find out that c minus a must be 1, and 2a minus c must be 0. As usual, I'm going to look for something that's easy to work with. The second equation says that 2a and c must be the same number. Putting this into the other equation, I find out that A has to be 1. The second that I know that, C has to be 2, and B is the negative of A, B is negative 1. This is the same result that we got by doing it the other way. The general form of such a thing is then you look at all of the linear factors on the bottom. If you have, say, a distinct linear factor, like the x minus 1, it contributes only the usual sort of term. I have 2 factors of x minus 2, so instead of just a constant over x minus 2, I'll have another term that has constant over x minus 2 squared. Because of the 5th power on the x minus 4, I'll have fractions with constants upstairs and various powers of x minus 4 downstairs, going from x minus 4 to the 1st power all the way to x minus 4 to the 5th power. I wouldn't actually ask you to work out one like this because obviously this is going to get a little tedious, but I hope this illustrates the pattern and tells you what to do when you have one of these rational function problems with repeated linear factors on the bottom. In what's to come, we'll look at what you do when you have factors in the denominator that are quadratic but don't have any real roots, so that you can't split them up into a product of linear factors. I hope everyone's having a good day. I'll talk to you again soon.